You said, "Oh, I'm not a philosopher. I'm a mathematician," but in your books and in your work, there are so many references to God that I think that you are also a great theologian.
Great, that's very kind of you. I was corrupted by Einstein.
Yeah.
Einstein mentions God all the time, but he says he doesn't believe in a personal God who looks after our affairs. He believes in Spinoza's God,
Yeah.
who manifests himself as the laws of the universe.
Yeah. Let's see if it is really that there is in Spinoza, but we need to discuss that.
I don't know, but Einstein mentions God all the time as if God was a friend of his that he discusses physics with.
Yeah. It's interesting because, but you needed to say just before we started this conversation that, oh, it's a metaphor, like if you were defending yourself, like, sorry, yeah, God, but as a metaphor. So what do you mean by that, by a metaphor? Because in fact, even the fact that you need a metaphor, first we could say first, isn't it everything a metaphor for humans? Because we don't have access to what is real in itself. That's even the reason why we put reality and real. It's not the same word. When we say reality, it's already a construct of what is supposed to be real that we don't have access to. So in fact, we are always using metaphors even to express the most simple things in a way. So what do you think about that?
Right. Well, it may be a metaphor, it may not be. I think that depends on who's listening, and even for me, sometimes I mean it one way, maybe sometimes I mean it more the other way. But God can also stand for sublime or the transcendent or the sublime.
Right.
Or the infinite.
Yes, exactly.
Or the incomprehensible.
And here we come to the subject. Infinite. But do you want to know about my theory about why Einstein said, in the same time he said that in a way he does not believe in a personal God, but he used God all the time. And my theory about why you say it's a metaphor, my theory, but it might be a very naive theory.
Yeah.
It's because you can't picture what you are actually doing as a mathematician, and you can't picture what he's actually doing as a physicist without what he calls God, but he doesn't want it to be mixed up with religion, with what was used to be like belief and things like that, because he is, of course, and you are a man of knowledge. Don't you think it is that? It's a way to try to, and in the same times, he needs these God, to say a word that is actually out of the picture in order to be even, I would say, reasonable.
Yes, well, Einstein is always asking himself, would God design the world this way? Would God design the world that way? But you have to remember that Einstein grew up in the late 1800s. And at that time, people still talked about truth with a capital T, about beauty with a capital B, about God or infinity. And there is this process, at least in some societies, of what is it called? The secularization.
Yeah, secularization. In France, we say laïcité, but it's secularization, exactly.
Right.
The fact that we tend to separate the place where we can believe, like of faith, with what is supposed to be rational on the other side, and we separate it. It doesn't have to be intertwined anymore.
Well, okay, but you have Pascal on the one side and you have Descartes on the other, right?
Yeah.
In France, to remind you that both points of view can be fertile.
Yeah.
And beautifully expressed in both cases.
And not something that could sterilize your capacity to produce knowledge, because Pascal was I mean, he was also doing mathematics.
He was a wonderful mathematician.
Exactly. So basically, he was both. Maybe we need to be both when we reach a certain level.
Well,
Otherwise, you're
yes.
just an engineer.
Yeah, well,
It doesn't mean that I don't like engineers. And
no, I've worked as an engineer also. That can be fun. But I think there's a question of why do we do science or why do we do mathematics? One is searching, some of us are searching for the sublime, for the reality behind everyday appearances, for the transcendent. I think it's impoverishing to not be able to use those terms. Now, it's up to each person if you take it as a metaphor or if you are actually a believer. I think each individual has the right to decide, and it may depend on the mood they're in at that moment and the topic.
Do you know, you pronounced already 3 times a word that I think is very interesting for our subject and to get closer and closer to our subject, which is the meanings of infinity, of the infinite. It is the word sublime. It's interesting because if you read Immanuel Kant, he has distinguished, maybe you're aware of that, but it's very interesting the distinction that he made. He said, on one side there is beauty, on the other side there is the sublime. And he said beauty is actually, and you see, if I say that, it's because it's directly related to the infinite. Because beauty is actually what is perfectly symmetrical, balanced. A beautiful face, it's because it's perfectly made, the 2 sides are well, there is some kind of an equilibrium that you can find, you can see it, you can grab it, and you feel it, and you say, oh, that's beautiful, because everything it is in its place and everything. The other way around, the sublime is different. On the contrary, the sublime can be something beautiful, but more than beautiful, something that in fact you can't even name, you can't even find, because it doesn't have limit, you can't find the limit. So it can be also the horror. And so the first reaction that you have in front of the beauty, it's admiration. You admire it, or you feel it's beautiful. But in front of the sublime, the first feeling you could have is actually terror, because you are impressed by something that just, overpass everything you could imagine. So because you're not even able to understand, to feel, to see what it is, and you see it's there, but is it even there? That it is sublime. That's in fact, the feeling of infinity.
Yes. Well, you talked about a beautiful face. I often think about beautiful ideas, beautiful mathematical ideas. And that's a very important element in mathematical creation. An idea has to be beautiful. Otherwise, what did someone, G.H. Hardy, say? There's no permanent place in mathematics for an ugly idea. Now, pioneering work is difficult, so an idea may start ugly, and then one tries to get to the essence of the idea and reveal its inner beauty.
But don't you think that we could make the distinction in mathematics? I'm not a mathematician, so I'm asking the mathematician. Between what is actually beautiful, because you find, like Kant will put it, an equilibrium, something balanced, something perfect in the way, like, you can see it, you can grab it, and you say, oh my God, I've solved something, I can see it, I can see the demonstration, everything is in its right place and everything. But what actually touched Cantor is something else. And it seems to me that he even realized that if I'm not, I'm really talking under your control here. I heard or I read in one of writings of Cantor, or somebody that wrote about him, I don't remember exactly, that he said that he was actually terrified by some of his demonstrations that about infinity, the different kind of infinity, and he said, I have demonstrated it, but in a way, I don't believe it, or something. I don't believe what I have actually demonstrated. Have you heard about this sentence? What is?
Yes, what was it that he had demonstrated? Was it that there were different infinities, there were bigger and bigger infinities?
And then the one that is can be, as you say, that can be a numeration, that can be
countable,
and countable, and he was able to demonstrate also that the whole could be smaller than the part, something like that, and it's like if he was able to demonstrate it, but that he couldn't believe it. He couldn't believe what he was demonstrating. Isn't it a way to talk about the sublime and not only beauty?
Well, Cantor's an interesting case because I think he was doing mathematical theology actually, but I don't remember what result was that he sees it but he doesn't believe it. Could it be that the points on the plane are more numerous than 1, 2, 3, 4, 5?
No,
it's a bigger infinity?
I think that is that. I think when he compares the line with the plane.
Well, the line and the plane have the same infinity.
Yeah, and already it's just like, in a way, he said, I think he couldn't believe it, and even if he demonstrated it. Because it's like, if you see it, you can't figure it. You can figure it even if the demonstration proves it.
Yeah, well, you have a one-to-one equivalence between the line and the plane. Yeah. So
it's the famous diagonal of Cantor.
The diagonal argument is something else. That shows that there are more points on a line than there are whole numbers, 1, 2, 3, 4, 5.
Okay.
That's the famous diagonal argument.
Yeah.
But the other side of the coin is that there are not more points on a plane than there are points on a line, even though it looks like they are. There is, if you take into account neighborhoods, because you can't do a one-to-one mapping that preserves neighborhoods. There's a whole theory of dimension. But as quantities, infinite quantities, they're equally big. But he has a beautifully simple proof that there are more real numbers than there are whole numbers. So that's more points on a line than whole numbers, 1, 2, 3, 4, 5. And that's the fact that there are infinities that are bigger than other infinities makes the theory interesting, Cantor's theory. Yeah. But then it starts to go wild because he gets bigger infinities and bigger infinities and bigger infinities.
Exactly, but you know, for a philosopher, what seems weird at first sight, and because it's weird, it's interesting. Because what likes a philosopher is to be amazed, to be astonished by something that other people will not pay attention to. And so I'm really amazed when I hear you, because that will mean, because when you think about something that is big or bigger, you immediately think that if it is big, when you see big, it's because it's finite, because it's big. When you think big, because when you say big, you are already referring to a limit that makes it what it is, saying it's big. But when you say, oh, it's a different infinity, it's a bigger infinity, you really have a hard time, if you're not a mathematician, I mean, so to say, to even understand what it means. You'll be tempted to say, oh, those mathematicians, that's just nonsensical. Because, you know what I mean?
Yeah, well, that's what makes Cantor's work so wonderful, that he shows that some infinite sets are equally numerous, like that you wouldn't expect, like the points on a line and the points on a plane. You think there are more points on a plane than there are on a line, but it turns out that you can make a one-to-one correspondence with the points.
Yes. It's amazing, these.
Right, but then there is this.
That's called biunivoque correspondence,
one-to-one correspondence.
One-to-one. In French, we say biunivoque. We say.
En français.
Biunivoque. The mathematicians, they say biunivoque. I don't know.
Well, that's the Bourbaki terminology.
Yeah, okay.
Cantor used an older
All right.
terminology that I guess
He said
I'm
one-to-one?
using. One-to-one correspondence was the old
that's
word.
binevoc.
Now what is
Exactly.
it? Bijection?
Bijection, exactly.
Right. That's
exactly.
the Bourbaki terminology.
Yeah, exactly.
Right.
Exactly.
So that makes his theory wonderful, but you get into problems. Cantor's theory has the same problem. You ask a child, is there a biggest number? You know, and then what happens if you add 1 to it? That gives you a bigger number.
Yeah.
So there is no biggest number.
Yeah.
So the same thing happens with Cantor's infinities. For any infinity, it turns out there's a much bigger infinity, and you can keep going and going and going.
So there is an infinity of infinity.
Yeah, well, you can make
because
one
if you
for
keep
some-
going ad infinitum, as we said in Latin.
Right. Yeah. So you start with the infinity of the whole numbers. Then you go to the infinity of the points on the planes, or the points on a line.
The part of the whole, the infinity of the part, right? Of the different.
Then there's another infinity. Well, the simplest way to get lots of infinities is to take the set of all subsets of a set. Gives you an infinite set. If you take an infinite set and consider the set of all its subsets, this turns out to be a bigger infinite set than the set you started with.
Yeah, exactly.
And then
It's
you can keep going, and you get a you get a sequence
Yeah.
of infinities. But guess what? You can then put all these into a bag, and you get an even bigger infinity that is bigger than all the infinities up to there. And then you can keep going.
It's what I call the parts. The parts that when you again you put the parts that are become.
Right. But you get into trouble because the proof that for any infinite set there's a bigger infinite set, which is the set of all subsets of the first set, gets you into trouble if you say, well, take the set, the universal set, the set of everything. That's got to be the biggest possible set. It includes everything. But then take the set of all subsets of that, and that gives you a bigger infinity. But how can there be an infinity bigger than everything?
Yeah.
So
that means that mathematics is actually bigger than reality.
well,
Yeah, it's what you actually demonstrated now.
Mathematical
it's what you said.
imagination
It's what you said.
is open-ended.
But I don't know what is imagination. I'm just saying, what you just demonstrated mathematically is that mathematical objects are more numerous, are bigger in themselves than the real world.
The real world.
That, what I mean, when I say the real world, is the only word that comes to my mind, but I mean that what I will put it in Kant word like phenomens.
Yeah, so Cantor's conception is essentially open-ended in statu nascendi, and it's paradoxical because you have a problem that there's a bigger set than the set of everything, which can't be.
But now,
yeah,
to try very modestly to overcome this paradox, because it sounds like a paradox, to say that there is an infinity that is bigger than the world itself.
well, you get out of it by saying, you can get out of it in some ways by saying the universal set is not really a legitimate set, but the fact remains that Cantor's conception is essentially open-ended, and it doesn't fit in with the Platonic idea that the world of mathematics is perfect, static, and eternal. Because what Cantor is doing means that for anything you imagine, you can imagine something much bigger and bigger and bigger, and this is like a growth process. And there is no prescription for any system you can think of for getting bigger and bigger infinities. There are infinities that are bigger than any one that can be reached by that system once you specify the system. There are even in infinite sets or cardinals which measure the size of the set.
The cardinal
They're called
system.
inaccessible cardinals, which means that there's no way to get to them from below. And then there are things called non-measurable cardinals.
It's always the question of a cardinal, actually. We did it, but it's always the question that the cardinal is always bigger. and bigger and
Right,
bigger.
the cardinal is a number used to
Yeah,
measure
yeah.
the size of an infinite set,
Yeah.
how many elements it has,
Yeah.
right? So the whole thing is wonderfully crazy.